Hello everyone, welcome back to the lecture on analytical modeling of energy storage devices under the title Smart Grids Basics to Advanced Technologies, and we will just identify what we are going to talk today. So, we will try to use this next 30 minutes on general model for energy storage, the modeling part. We will talk about bit of different terminologies, how they are being used, and we will also try to understand the equivalent mathematical model of batteries, and then we will talk about how the batteries got degraded over a period of time and its performance or not remain same throughout the life. Then we will also talk about capability curve as per the real and reactive power available to us through energy storage, and they will also talk about battery modeling methods and its evaluations. We will also talk about finally the equivalent circuit model of a storage device. Now, the general model of energy storage, as you could see, it mainly consists of a storage medium, number one, and then it has a power conversion system, and then there is a BOP, that balancing of the plant. So, these are the three main components of energy storage system. Now, you can see that there is a grid which is a system bus in which the energy storage devices has been connected, and this is considered to be a perfect ideal scenario. But when we try to understand more into it, possesses a bit of losses. First of all, it starts with actually charging and discharging losses, and then it has idling losses, and then you will have bit of converter losses through inverters. And so, this is basically my representation of a energy storage, including different type of losses it undergo during both charging and discharging phenomena. Now, there are a bit of terminologies which are important to understand more about the future discussions. First is ideal storage, so which represents an ideal lossless energy system, because if you say it is a 10 kilowatt system, which is really not true, it cannot give you 10 kilowatt, but theoretically it is 10 kilowatts, which is ideal storage to me. Moving to charging and discharging losses. What is charging losses, discharging losses? So, we claim during the charging and discharging pattern, storage devices do experience bit of losses, and it represents the charging and discharging losses associated with the conversion from the storage medium, example battery, to electric energy and vice versa. Now, there is an inverter, it allows dispatching reactive power, modeling the inverter losses and limiting the rate of charge and discharge based on its ratings. What is state? Represent the state in which storage element operates. The three possible states are charging, discharging and idling. So, that means there is nothing happening. Okay. Idling losses, even the battery is ideal, still you experience some losses, represent storage self depletion losses and auxiliary loads, because locally it has to meet some of the components operation. Now, here I want all my student friends to focus on the mathematical modeling of energy storage. So, if you say energy stored at a time t, which is my E t plus 1. So, energy stored at time t, which is t plus 1, E t plus 1, which is the energy available at time t minus, that means reduced to delta t times P dCHT upon the efficiency minus PCHT multiplied by efficiency. Now, what is PCH and PDCH? PCH and PDCH represent charging and discharging power. However, E is my energy stored and E rated is my rated energy capacity, and UCH and UDCH are nothing but charging and discharging status of the battery. So, what we are saying, the charging status plus the discharging status of a battery must be less than or equal to 1, either it is a 0 or 1 or ideal. So, I think no case it can be more than 1. So, the status of initial and final energy over a period of 24 hours will be given as 50% of the rated power, and the depth of the discharge which can be considered as DOD, which is 1 minus E upon E rated. So, the previous statement what you are saying, assuming that the battery its initial position, it could be 100% charge or it could be 100% discharge, but ideally what we are considering that the starting and ending period of a day, the battery should not be at 0 or 1 state, it must be 50% of its rated capacity or its energy stored will be equal to 50% of its capacity. That is the theoretical assumptions being taken here. Now, when you talk about battery degradation, now here the previous slide what I wanted to tell you, the value 50% do not get confused. So, what we wanted to say, no time when the day begins or during the end of the day, we are forcing the battery to have certain amount of energy within it instead of completely discharging and completely charging, which is not acceptable. So, the ideal value could be 50%, that is what actually I wanted to highlight here. Now, when you talk about battery degradation, that is battery aging, calendar aging and cycle aging. So, battery aging is a non-linear process that depends on time, temperature, depth of discharge and the number of charging and discharging cycle. Very importantly, it depends on the number of times you charge and discharge that decides your life. Calendar aging, that means inherent degradation over time. The rate of degradation depends on temperature and SOC. Okay. So, it is a natural degradation process, how it has been exposed to heat and how its temperature control being managed. So, that will decide your calendar aging. Now, what do you mean by cycling aging? Cycle aging means life lost each time to battery, life lost each time the battery cycles between charging and discharging. So, the life got reduced by each cycle of charging and discharging is known as cycle aging. And finally, ESS lifetime, we define degradation per year, which is nothing but the number of cycles divided by cycle to failure will give me the degradation per year, and indirectly the lifetime in a year is nothing but the inverse of degradation. Now, this is we are talking about capability curve, and there are two different characteristics we will be focusing on. All of you please try to understand these variables. This line represent kVA, red dotted line is kilowatt rated, and then kVAR maximum, kVAR maximum ABS, operating region and operating points. Now, depending upon different operating points of your charging and discharging and real and reactive power drawn or injected, you can see if you connect those dots. So, this will be indirectly my actually PQ characteristics or the capability curve, especially when you operate with PQ curve with constant power factor, and you can also plot a characteristic PQ curve with constant reactive power rating. So, you can experience a characteristic of this nature. So, for real time analysis, we can draw such characteristics and allow the battery to operate in which mode, and the region of operation can be predefined. Now, when you talk about battery modeling methods evaluation, so if you focus on electrochemical, the advantage of electrochemical battery modeling is which is high accuracy. The challenge here is high computational burden, high nonlinearity and excessive parameters, which is a demerit to me, and the application will be cell design. And equivalent circuit, which is balance between accuracy and complexity, easy of online implementations, and the problem here is limited accuracy estimation of battery state energy management, grid connected energy storage will be one of the application. Now, if you go for the third model, which is an empirical model after equivalent. So, we can talk about 3 different models: electrochemical, equivalent circuit model, empirical model, and each and every model has certain advantages and limitations. So, we need to see what are those. Now, in case of empirical model, we will have actually low complexity due to linearity, ease of online implementations. However, the limitations as high as low accuracy, lack of insight of battery dynamics, and its application could be grid connected energy storage. Now, focusing on equivalent circuit model, it is 2 time constant TTC representation of the resistor capacitor ladder circuit model. So, you could see this a DC voltage source, and you have a shunt resistance, and you have a series resistance, and then RC in parallel. So, this is equivalent circuit model, which is quite accurate. So, R self discharge denotes the self discharge energy loss when batteries are stored for a long time. So, this resistance that you could see as R self discharge denotes the self discharge energy loss when batteries are stored for a very long time. You might have seen, after using a battery, if you keep it for a very long time, then you could experience self discharge. The more RC circuits, the more RC circuits, those ones, you can even create one more. Okay. We can keep on doing it. So, the more RC circuits are used, the better the model can capture the transients of the battery. And VOC, this one, is a dependent voltage source representing the open circuit voltage OCV, which is the battery's terminal voltage after the battery is fully relaxed. And similarly, the resistances R1 to Rn are the leakage or transient resistances, and C1 to Cn are the corresponding dynamic capacitances. And I think you need to read a lot of references to understand more about those mathematical modelings. So, with this understanding, I am very confident that once you go through this in detail, probably you can understand more about complicated modelings and its applications. But nevertheless, the idea that you have gained today on the energy storage devices and its mathematical modelings and general modelings, as well as the analytical modelings of energy storage devices, will help you to understand its future applications and demonstrations. Thank you very much.